Hello, hello, hello.
Thank you. Yeah, I will take. Which one? On. Okay. Thank you. I am thankful to the Professor Radhikari for giving me opportunity to speak here. Okay, I am going to start with very elementary, already you know, but the extensions you might not have seen. Okay, I am going to use Burnside lemma for proof. So, Formality theorem, which is well known in elementary number theory as well as group theory. Already you have seen in Shauli's lecture. So, given a prime number p, the congruence a power p minus 1 congruent to 1 modulo p has solution for all a co-prime to p. Okay. Suppose if we want, instead of just co-prime to p, we want all residue classes modulo p, then we just twist it this way: a power p congruent to a modulo p for all integers a, either congruence class or all integers a. So, okay, so this was generalized by Euler for all natural numbers. For any given natural number n greater than or equal to 2, the congruence a power phi of n congruent to 1 modulo n for all integers a which is co-prime to n exists. Okay. So, this congruence is true for all co-primality class. Okay. The question is, the way we have done for Formality theorem modulo p, for all that congruence holds true for all integers a, similarly whether we can do it here or not. Okay. The problem is, what is the generalization of Euler's theorem which holds true for all integers, not just co-primality classes alone. Okay. Okay. Not well known, this is what I feel, but there are 3 statements at least I knew of which does this job. This is elementary, it uses just basic group theory, a proof. Okay, in this lecture we prove 3 extensions. First 2 is this kind. Okay, n greater than or equal to 2 is an integer, a is any given integer. This sum of a power the GCD of k and n, where k runs over all the residue classes modulo n. So, I am fixing z mod n z 1, 2, 3 up to n, that is my kind of. Okay. Then a power the GCD of k comma n, this sum is divisible by n. This is an extension of Euler's theorem. Why we will see. So, when n equal to p, you see the sum is the GCD, if you look at it, except 1, rest all GCD 1, because only when k equal to p it is p, otherwise all are 1. So, if you see that, it is just Formality theorem, and it holds true for all given integer. Okay. And by just fixing GCD of k comma n is a divisor of n, therefore, you fix d as one of the divisor of n, then we can get the second one. This extension is n greater than or equal to 2 integer, any given integer a, we have this congruence which is true for every integer. Okay. This you see when we fix k, the GCD k comma n fixed integer divisor of n, then how many such how many times it would have been appeared in that above sum? Exactly phi of n by d times. This is second extension is nothing but the first one only, just a rearrangement. Okay. So, this sum is divisor sum d divides n phi of n by d a power d congruent to 0 mod n. Okay, we will give this proof and then we will go to the third extension. The proof is going to come from Burnside lemma. So, I would like to recall, okay, G is a finite group, X is a finite set, we consider the group action of G on X. We recall the following definitions. The orbit, given element X in the set capital X, orbit of X is nothing but the group G dot X, where G is varying over all the group elements, which is a subset of X. And the stabilizer group of this action for the given element X, set of all G such that G of the action is trivial. I mean, the G dot X equal to X rather, identity, okay, fixing. So, set of all group elements fixing the element X, that's it's a subgroup. Okay, one more definition is it's a kind of, that is the previous stabilizer group is coming from elements, I mean given a X, we are calculating, we are counting all the elements of G which fixes X. Here we are just fixing a G and we are taking all the fixed points, G dot X equal to X. How many X are there? That we are collecting. That is, we call it NG. That is otherwise fixed point of G. Okay. So if the identity element is denoted by E, then NE is nothing but the complete, because this is a group action. Okay. The counting lemma is known as Burnside lemma, the following one. See, it counts what is the number of different orbits. Suppose n is the total number of different orbits of the group action. This n can be given by, is nothing but the average of the fixed points. That's what it says. So 1 by cardinality G, sum over all the group elements Ng. Ng is nothing but the fixed points of G, the number of fixed points of G. Okay, we will prove this. In order to prove, okay, so we are looking at this set S, which is a pair of elements G comma X inside G cross X, such that G dot X equal to X. We count this in two ways. One, we fix G and we count number of elements X. Similarly, we fix X, number of element G, satisfying this. Okay, first we fix G and count all the X such that G dot X equal to X, which is therefore, you see, once you fix G, then counting all X, that is nothing but number is Ng, that is a fixed points. Therefore, total number of Ng is nothing but this cardinality S. Now we will fix X and count number of G's for which G dot X is X. This is nothing but stabilizer cardinality. Okay. So the cardinality S is sum of the cardinality of stabilizer group. So therefore we get these two. Now we have to apply the orbit stabilizer formula. Okay, which is orbit of the cardinality of orbit of X is the index of the stabilizer. So if we apply, what we can get is this formula. Okay, so the left hand side average of the fixed points, this is equal to sum of 1 by orbit of X, the cardinality of orbit of X, where sum varies over all X. Okay, this is what the last equality, this is what we get. The left hand side is correct one. The right hand side we have to check whether it is total number of orbits comes or not. Okay, for a given element X and Y in the same orbit of X, then the cardinality of both orbits are same number. Okay, so therefore what we get is, if n is the orbit of X, then there are n elements for which orbit of Y is going to be n. So therefore the sum will give 1 precisely. Okay, so how many, this is a counting function for one orbit. So this particular thing. So therefore total number of orbits I would have got it by varying X over all the elements of X. Okay, so therefore this is same as the Burnside lemma. Okay, next extension, we are going to extend this Burnside lemma a character version. That is the reason I went through this proof. Okay, first application of Burnside lemma, we prove the following. G is a finite group and A be a given positive integer, then we have this particular congruence. The congruence is sum A power cardinality G by order of G, little g. The sum is over little g. This sum is divisible by cardinality G. This is what we want to prove using Burnside lemma. Okay, so first in order to use Burnside lemma, somehow we have to, for a given g, because this sum is varying over g. So given g, ng is going to be like a power cardinality g by order of g. This is what I am going to connect. Okay, once we connect ng equal to a power cardinality g by order of g, then I can use Burnside lemma, immediately answer will come. Because Burnside lemma will say the average of ng is going to be cardinality g. So therefore, this sum of ng is nothing but 0 modulo cardinality of g. So what one has to prove is ng is nothing but a power cardinality g by order of g. Okay, so for that we are going to take some group actions, and using that group action we will get this. Consider the group acting on G acting on itself by left multiplication, G comma x going to G times x. A is a given positive integer, therefore we take the set S. I could have given x, so take the set S 1, 2, 3 up to A, since A is a given positive integer. So we collect all the functions from functions f from G to S. Okay, so this is a set of all functions on G to S. Okay, so we can, since already we have action on G, we can induce the action, the same action of G onto this set S, which is usual. Okay, so if we take one element, we want to define an induced action on C, the set of all functions. So we take one element in G, and we G dot f is a function. We want to define, this is a function, it's supposed to be a function on G to S. So how we define? We define f of G inverse of H. Okay, this is indeed an action, one can check it on this set C. So for a given G, first we shall count, because our interest is ng, we want to count ng, the number of fixed points of G. So we shall count the number of f, a number of functions which are fixed by G, given G, under this action. So first, okay, so what we have to check really, number of fixed points of G, G dot f equal to f, number of G dot f equal to f, that number of f's we are looking at. So G dot f equal to f means for any given h in G, f of G inverse of h equal to f of h. This is what the fixed point of G it means in this action. Okay, this is what the kind of definition just. Okay, what we claim, this is easy. F is fixed by G, element G, if and only if f is constant function on every coset, left coset of the cyclic group generated by G. Okay, why it is just suppose the given element G fixes f. We want to check whether the left coset, given a left coset, this f is constant or not. We want to check. Okay, take any element h1 in the left coset, arbitrary element. Then so h1 belongs to this left coset. It means h1 look like g power I times h. So therefore f of h1 by definition of the action we can write like this, f of g inverse of h1. Okay, now we check what is the value of f of h1. F of h1 is going to be f of g inverse of h1, but h1 I can replace it by g power I times h. So I can go down to, it becomes f of h, okay, at the finite limit stage. So for any element of this left coset, the function is constant. It depends only on the representation h. Okay, so it is constant. So f is constant, and similarly, if f is constant on the left coset, then automatically it will come. Okay, this is f. G fixes f. Okay, what is this says? It counts. It's using this claim we can count a number of the ng. So given as G in G, Ng is the number of the functions f that are fixed by G. So by the above claim, it is equivalent to say that Ng is the number of functions such that f is constant on each coset of the cyclic group generated by G. Okay. So since f is a function from G to S, so Ng has to be cardinality of S power k, where k is the number of distinct cosets of the given G, cyclic group G. Okay. Because it's a function, it has to be constant on each coset. There are only k many cosets are there, therefore we can get fixed points only, this many functions only, mod cardinality of S power k. So cardinality S is nothing but a, so a power k, okay, where k is the number of cosets of G. I mean there is cyclic group generated by G, little j. Okay, this k is nothing but the index, therefore cardinality of G by the cardinality of the cyclic group, which is order of G. Okay, so therefore we have got what we have got, Ng equal to a power cardinality G by order of the element G. Therefore by Burnside lemma, so we can get this particular sum is divisible by cardinality G. Okay, it's induced action, then we get this by Burnside lemma. Okay, so we want to prove the extension 1. So we take G to be Z mod n Z, cyclic group of order n in the proposition 1. So A is given integer, therefore A has to be modulo n, A has to be lie inside 0 to n minus 1. If A is 0, then we are done, because if you see the proposition, I will go to that. What is the extension statement? What we want to prove. Okay, this is what we want to prove. If A is 0, then nothing to prove, everywhere 0. So we can assume that A is 1 to n minus 1, because we are working with modulo n, it is enough to. Okay. So it is, we can assume 1 to n minus 1. So we take the representation of Z mod n Z as 1, 2, 3 up to n. Okay, we don't want 0 to n minus 1, because the way we have taken the sum, because we want to use the GCD etc. So this is the best one. This is the representation. So for given integer 1 to n k, the order of k in G is n by the GCD. This is in the cyclic group, this is the order of element, this is n by the GCD. Okay, GCD of n comma k. So therefore by the proposition 1, we have sum from k to k equal to 1 to n, a power the cardinality G is n divided by the order of the element. Here element is k, order of k is nothing but n by the GCD of n comma k. So therefore we get it. Okay. Okay. So next proposition is already I have told, just fix 1k, then fix one divisor d, because GCD of k comma n is going to be a divisor of n. Therefore fixed divisor, how many k's are there such that the GCD of k comma n is given d. That is precisely phi of n by d, because the GCD of k comma n is d if and only if k by d comma n by d is 1. GCD is 1. So this is precisely this many number. Okay. Therefore by adjusting the likewise term, this inequality, this congruence will come. Okay, the third extension, this is mu of n by d. This is 2005 it was proved. For a given integer n, a is any integer, we have the sum over d divides n, mu of n by d, a power d. This is congruent to 0 modulo n. This is true for all a, and mu is the Mobius function which we have seen yesterday's class also. So mu of 1 is 1, where mu of, if m is more than 1, then it is nothing but minus 1 power L. If m is a square free integer and L distinct prime is there, otherwise it is 0. Okay. In order to prove this, we need to extend. Okay, so why this is going to be, first we will see why this is an extension of Formality theorem. So when we take n equal to prime power p power k for some prime p and for some positive integer k, then the extension, this third extension gives you a power p power k congruent to a power p power k minus 1 modulo p power k. So when k equal to 1, if you see, it is Formality theorem. So p square, this is the way to extend for all integers a. Okay. So just why? Because you just calculate the divisor of p power k, only twice you will get square free, otherwise everything is going to be square full, therefore it will be 0. So only 2 terms survives, rest all 0. So you will get this. Okay. So in order to prove this, we want to extend the Burnside lemma for a character version. Okay. So first we need to extend a lemma with character. So what is character, and proposition 1 also with character, then we apply the same pattern. Okay. Let G be a finite group that acts on a finite set X. Under this action, for any x, okay, I am just changing the notation just because orbit I have to keep writing n number of times. Ox is nothing but the orbit of x. Rho is a character on G, so it means it's a group homomorphism from G to C star, multiplicative group C of C. First definition, suppose action is given and orbit is given. Orbit of the action of G on X is given, we say, and the character is given. Okay. We say this orbit is a rho good orbit. Okay. So when we say, if the stabilizer group Gx contained in the kernel of this rho, okay, for any x inside the orbit. For all x inside the orbit, we look at the stabilizer group, whether it is contained in the kernel of the given character or not. Okay, first we observe, if you have G for one x, if Gx is contained in kernel, then it is true for all x. Why? Because kernel is a normal subgroup, and 2 elements if you take in the same orbit and the stabilizer groups are conjugate, therefore if one is there, other will be there. Okay. So it is enough to prove it for one element of the orbit. Okay. When the rho is a identity character, suppose rho is a trivial character, then everything, I mean whole G is going to be there, so every orbit is going to be rho good. Okay, that is what Burnside lemma is. This is just refining it. Okay, every orbit is rho good. Okay, we prove the generalization. Okay, 2005 American Monthly, Isaac and Bernanke. Same, only thing. Okay, so G is a finite group acting on a finite set X. Rho is a given character of on G. N is the number of rho good orbits. Instead of all orbits in Burnside lemma, all orbits it was counting. Here it is number of rho good orbits. Then N is nothing but kind of twisted average here with rho. So this 1 by cardinality G, sum of rho G N G. N G is the number of fixed points. That is same definition. Okay. Okay. So we are going to apply in order to prove that we will apply Burnside lemma in one particular action, so that this comes. Okay. First, since n is number of row good orbits, I am just taking m to be the number of total orbits of this action, given action. So that's what I have written it in words. Capital M is the natural number, which is the total number of disjoint orbits. Okay. So what we have to count, the number of, among that number of row good orbits, we want to have this formula. So we start with the general orbit and we try to compute a counting function for row good orbit. Okay. So that then we sum it over all the, with that counting functions, we sum it over all the orbits, then we will get that. So this is, we start with the right hand side, I mean fix, oh, I change the notation again. So yes, so given a orbit, fixed orbit O, this sum varies over little g, rho of g, this ng, fixed points of g, I call it ng, this is, okay. This rho of g is a complex number, which is counted this ng times in this sum. Okay. No. Given a g, fixed g is nothing but set of all x inside O, gx equal to x. G dot x is x. It's a number of fixed points inside the orbit. Okay, that's what it means. Okay, so it is counted once for each pair x comma g as this way. So I am going to rewrite in terms of the definitions this right hand side sum. So this SO is nothing but first one is usual one only. So this ng I have written it in terms of just a formula. Ng means it counting number of x inside O such that g dot x equal to x. That's what I have written in the second sum. Then I am interchanging the sum. It's all are finite sums. I am interchanging the sum. Given a x, I am counting number of g's such that g dot x equal to x. That is nothing but my stabilizer group will come in. So this means where I have to count with rho g, that many kind of that number. So this is just a interchange of sum. What we get is this. Now you see sum over rho of g, where g is varying over all the elements over the stabilizer subgroup. So I can, since rho is a character, if I restrict to gx, this is going to be a character, and I can apply my orthogonality relation on characters. Okay. So since stabilizer gx is a subgroup of g, rho is a character on g. Okay. The stabilizer subgroup and rho restricted to gx is a character. By orthogonality of characters, what I can get, I can evaluate this sum. This sum is nothing but 0 if the gx is not, the rho is non-trivial. This when it is 0 is this rho is non-trivial on gx. Non-trivial means it is gx is not inside the kernel. Okay. So when rho is trivial means the gx is completely inside the kernel. So therefore this is the orthogonality of character. Okay. Now I plug it in. So okay. So okay. When I plug it in, then the set of all so I sum over x inside O, and whenever gx inside the kernel of rho, I get cardinality of gx. Okay. Otherwise, I don't count at all. Those x only I am counting. Okay. That's what the SO does. So the cardinality of gx is nothing but by stabilizer orbit stabilizer formula, the cardinality of g by cardinality of the orbit. This is true for all x. Therefore, so what we get SO is nothing but is a counting function for O is rho good or not. The previous thing will tell you this Gx is inside the kernel of rho. It means that orbit is going to be rho good. Okay, that's what it says. Okay, this is a counting function for a precise given a orbit when it is going to be rho good. That is precisely this is. Now I have to sum it over all orbits. Okay, so no, you then by sum it over all orbits, number of orbits, then I can apply my Burnside lemma. That will tell me this. Okay. That is true, but I will be applying original Burnside lemma also here. Yeah. Yeah. So because that counts total number of orbits, here we have got a counting function which kills that, whichever is not rho good. Okay. So, yeah. No. Here it's not L2, sir. This is normal. I mean, this is some. You take a character and sum it over all the elements of the group. Then it will be whether character is trivial or non-trivial. Depending on that, it is 0 or the cardinal dg. That's okay. So same. I mean, we have done the same application without rho. Now we are with rho. We are doing the proposition 1 without rho is trivial character. Now with non-trivial character we are proving. Just same way one has to. G acts on itself by left multiplication. We can induce the action of G on C. C is the set of all functions from G to S, because A is a positive integer given, S is nothing but 1, 2, 3 up to A. Okay, just in the as just a ditto proof of. So for this induced action, for each G in G, what we had Ng is nothing but the fixed number of fixed points of G is nothing but A power cardinality G by order of G. That's what we had in this action. Here, okay, the same thing I am telling. Okay. So therefore, by the generalized Burnside lemma, because what we can get is this n is the number of rho good orbits formula. Okay. So since already we know what is Ng is going to be, Ng is nothing but A power cardinality G by order of G. So therefore we just plug it in, we get this same ditto proof, just because we replace the usual Burnside by character version. Okay. In order to get that extension, we need one more. So this is must be known, known to students. The sum of all, given n, natural number n greater than or equal to 2, the sum of all the primitive nth roots of unity, this is going to be the trace of, if zeta n is the primitive nth root of unity, trace of zeta n is nothing but sum of all the primitive nth roots of unity, that is nothing but mu of n. Okay. This you can prove it through Mobius inversion formula. Okay. So we are going to prove that third extension. Let me recall what we want to prove. Okay. So we want to prove this congruence in holds for all A, all integers. So mu of n by d, A power d, sum varies over d divides n. Okay. This symmetry function is 0 modulo n. Okay, here we take G to be the mu n. Mu n is the cyclic group of order n, consists of all nth roots of unity, and rho is the character from G to C star, identity character, identity map only. I am trivial character I am taking here. So after taking trivial character, we induce the action, no, we take the action G onto itself by left multiplication, and we can assume that integer is 1 to n, 1 to n, n minus 1, because 0 modulo n it will be, otherwise it will be, so 1 to n minus 1. Okay. So by proposition 2, what we had is a sum of rho of G a power n by order of G. This is 0 modulo n. Okay. But G is, you see, rho of G we want to see. So G is a nth root of unity, because our group is mu n, nth root of unity. If the order of G is D, then the coefficient, what is the coefficient of a power n by D? The coefficient of a power n by D is the order of all the primitive root of unity, that dth root of unity. So if I likewise term, if I just sum it, then what I will get the trace of that particular the sum of primitive dth root of unity I will get for a fixed D. Okay. So therefore what I will get is mu of D. This sum is written as, this sum is nothing but sum of mu of D a power n by D. Okay. That is 0 modulo n. Okay. Okay, this references, I have not given, is okay, references, there are 3 articles. One is, you must have seen K. Conrad, n number of articles he has written. One is on this also. The second one is the same group action Burnside lemma, the J.P. Serre 2003 paper in Bulletin of American Mathematical Society. That is readable paper, but his application is, I have not gone into, his application is in the arithmetic, algebraic number theory side. He will calculate the density of set of primes for which it doesn't, the given irreducible polynomial has no root, okay, modulo p. Okay. Such a density he will calculate using Burnside lemma extension, that is Jordan's theorem. He will improve the Jordan's theorem by just then he uses that. It's an elementary way he proves that, and he gives more application in topology also. Whatever I read is algebraic number theory side. Then this is an American Math Monthly paper 2005. That's, I finished it early. That's it. This Isaac and Purnaki in 2005 American Math Monthly. Yeah. 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 Because no, maybe okay. That's while lecturing I was also thinking what is happening here. Okay. So okay, if it is a trivial character, every orbit is going to be rho good. That is correct. When we apply, it was a trivial character clearly. Identity character. No, not a trivial character. Just because we have taken G to be mu n and we send it mu n itself, not sending to 1. Yeah, so trivial means there it is 1 only. Yeah. No, no, this is mu n to mu n. So, no, finite group if you take, then the image is going to be root of unity only in C star. So, therefore, identity map is a character. Yeah. Restricted to G. Restricted to G. No, I told trivial. That is not correct. Yeah. Yeah, otherwise, Burnside lemma would have been used. Why this is needed? Okay, okay. No, no. There is only one paper of J.P. Sir written in English. That is this paper only, 2003, Bulletin of American Mathematical Society. Jordan's theorem, on a theorem of Jordan. That is the title. He proves actually Burnside lemma also gives a proof, and then he will prove Jordan's theorem, and then he will give an improvement little bit. Yeah. No, no, complete. No, I just showed you why it is kind of generalization. Just looking at the prime powers, you can see that. It is true for all n and for all a. You can for a given n, you just take only the co-prime classes, whether you get the thing or not. If a and n are co-prime, whether you get the Euler's theorem or not, you check, you will get it. $110.